Good morning, class. Today we're going to be working with testing. So we've got a exercise that is a simple game called Lobster Pot. And if we were to run this game, just to give you a quick demonstration, should be a fairly familiar one to many of you. It is a take on some classic childhood games where we are guessing a phrase and guess a character, and that was not the right character, so now my lobster has its claws drawn. That was a good guess, so that one works. That one is in there as well, as is that one. Oh, but an S is not, so now I got my little lobster eyes, and my little lobster body, and a little bit more of my lobster body, a little bit more, and oh no, I've got the entire lobster drawn, which means I have lost the game. So that's what we're going to be writing a test solution for, our test project. So we have, this is just a console project. We have the three files, the program file that does kind of the initial control. We have this game logic class, which represents the logic of our game, where we have a secret phrase and what's been revealed, the number of guesses we have in a list. We're using properties to expose some of those. So we, for example, reveal the phrase. We create a string from this array of characters to show what it currently is. Wrong guesses, we have a public getter and a private setter. So we can read how many wrong guesses have been made outside of this class, but we can only set it from within the class. We're returning a character array, which is all the guesses that have been made, and that is this private guess list guesses. We convert that to an array and return that. And we have an is1 property, which is a Boolean, and we basically just check to see if there are any spaces still inside this revealed phrase, or not spaces, underscores, which indicate an unguessed character. So as long as there is at least one of those, we have not won. And we lose when the wrong guesses reaches 7. We also have a Boolean for in progress, which basically we check to see that the game is not won and the game is not lost. And then we have the constructor, which is where the heavy lifting is being done. We bring in the secret string. We create two character arrays for the secret phrase and the revealed phrase to be the same length as that string. We iterate over that string and pull out each one of those characters. For the secret phrase, we are putting in the exact character. For the revealed phrase, we're actually, depending on whether or not that was a space we just looked at, we're either copying the space straight across, or we are using the underscore. And then we have the other piece of our workhorse, which is the guess method. Takes in a character, adds it to the previous guesses. We initially set a flag to false. We iterate over the entire word, and if that secret phrase, that particular character in the secret phrase is the character that was guessed, we go ahead and set that in the revealed phrase at that position, and we go ahead and set this flag to true. And we use this flag because we can actually go through, there could, rather than breaking and returning from here, because there could be multiple occurrences of that character, we want to make sure we catch them all before we back out. And then we go ahead, and if it's not found, we increase the number of wrong guesses by 1, and then we return whether or not we found a character. So if that guess was a correct guess or a wrong guess. We also have a static class render, which draws our different pieces of ASCII art for the lobster pot and draws the revealed phrase, including those underscores. This basically just adds spaces between those so they're spaced out so you can see the different underscores. And then we also have the draw guesses, which kind of draws it in this array-like format so we can see what guesses are there. And then the actual program code, we pull in the secret phrase from this text file. So we open that file and we read all of the file's contents, and then we split that on the new line character, and then we go ahead and basically create a random number between 0 and the length of that phrase array. And then we go ahead and create that new entry, and we go ahead and execute trim on the line that we pulled out of that secret phrases text document to take off any new lines or spaces that are on either end of that phrase. And we go ahead and welcome our player to the game. We have a loop while that game logic is telling us that it's still in progress. We're going to draw the pot. We're going to reveal what we have already shown in the phrase, tell them what their previous guesses were, ask them to guess a character, read that in from the console. As long as that's not the escape key, if it is, we break immediately out of the loop, and then we clear the screen. If the guess is, or then we go ahead and take the character that was keyed in, we check to see if that's a valid guess. If it's a good guess, we get a great guess. If it's not a good guess, we get this, oh no, things are heating up message. We're also playing a couple beeps through the console, so if your computer has a hooked up internal speaker, so this is not the headphones, this is the actual system speaker, it might make a little beep for you. And then we draw our pot, or actually when we get out of this loop, we'll draw the pot one last time. We will tell them if they won or if they lost, and we'll thank them for playing. So a very simple game, but one that nonetheless we might have made some mistakes in. So that's what we're going to do, is we're going to test the game logic and make sure that that works the way we expect it to. So we're going to do this by adding a new project to our solution. And that project type, we're going to use an XUnit test project. And we'll call this testing, actually I'll call it lobster pot tests. This creates us a new project. It goes ahead and gives us a unit test. Let's rename this class to game logic tests, which is what we're going to focus on for today. So this is, we're going to write tests of this logic. Now, tests with XUnit are just methods in a class, so there's not anything super special about them. We need to bring in the XUnit namespace, and in that there is the assertion object, which allows us to do all kinds of assertions. And the other thing that's in there is these decorators or attributes, which are metadata, which we can put above any function, and it just goes in square braces. And this metadata provides some kind of special instruction to the constructor or to some other tool that's reading this program. So what is going in those brackets isn't actually usually used in the actual code. It's used by the compiler or other programs that are reading this to interpret it. And in this case, this is used by the test runner to actually identify this method as a test so that it can be shown in, if we go into the Test Explorer, for example, in Visual Studio, it reads in and looks for all those things that are marked with either test or theory. And if we go in, we have game logic tests, we have test 1, and unit test, that's because we changed the name, but we haven't rebuilt the project yet. It's still picking up the old one too. So when we rebuild, that will go away. Or actually, maybe even when we just save. I think we're going to have to build it for that to get undiscovered. And then these functions, we want these to actually reflect what we're actually testing for. So what kinds of things do we need to test for? What do we need to be thinking about in terms of this game? Well, a good place to start is think about what these different properties in our game logic should be when we first build this class. So probably a good one would be previous guesses. Let's start with previous guesses. So when we first build this game logic class, the player should have made no guesses at this point. And if that's the case, we would expect this array to be empty. Guesses should be empty at start of game. Seems pretty straightforward. Now, in order to actually test the game logic, we have to create a game logic class. And notice that it doesn't know where this game logic is coming from. And that's because it's coming out of this lobster pot test. So we actually have, or sorry, this testing exercise. So we need to add that as a dependency here. So we'll add a project reference. And we are going to link to that testing exercise project and click OK. So we have now linked those two. And we're also going to have to do a using statement. And we want to bring in the namespace that that game logic is in. We scroll up, that's testing exercise. We bring that in, and now we're happy, except game logic needs a string. So we can go ahead and construct that, and then we'll check game dot previous guesses, and we would expect this to be an empty string, and we're going to make sure that that's the case with an assert. So these asserts are defined in that XUnit library. And in particular, if it's something like this where it's an enumerable, there is an empty that goes with that. So we can check to make sure that that is empty, and that should return that fact. Now, if we run all of our tests where we discover that, it shows that we guess should be empty at start. And indeed, that passes. Looks like everything worked. So we're in good shape there. Now, if we go back and look at this, though, there is something a little interesting here, maybe even a little fishy. We provided an empty string as our secret phrase to guess. Now, I'm not sure about you, but guessing when there's no characters to guess really doesn't sound like a lot of fun. So we might think, you know what, I think we should actually make sure that we have to have some minimum number of characters. So maybe public void secret phrase must be at least, what do you want to say, 5 characters? 5 characters long. Alright, so we would want to be able to check that a game logic game equals new game logic. And then we would expect this to probably throw an error, would be my guess. So we'll do an assert dot throws, and we could look for a specific exception. So we'll probably want this to be a system dot argument exception, because an argument exception means something was wrong with the argument being passed in. In this case, the argument being passed into our constructor. And then notice we have to supply an action. An action is kind of like a function that we can pass around. So it's expressed usually using lambda syntax, but we can think of it as a function. These are the parameters that are being passed into that function, and then whatever goes in the curly braces is the body of the function that gets executed. So in this case, we are going to create a new game. Go ahead and rewrite this using the templated version. So we have, this is what we're expecting to throw. This is the logic that's going to get us there. Now we have to provide some strings that are not at least 5 characters long to put in here. And we could do this as a fact, but this is actually maybe a better fit for the other category, which is a theory. And with the theory, we also have to supply inline data. And we can supply as much inline data as we want, but what goes in these parentheses is what's going to be passed in as our arguments here. So we would want a string secret, which we'll pass in, and we'll put this in here. So this is going to basically create that game logic using whatever secret we put in here. So one of the cases we wanted to test for is the empty string. One of them maybe 1 character long, maybe one that's 2 characters long. And maybe one that's 3 characters long or 4 characters. Really, as long as we have a good sampling and we get 1, 2, 3, 5, what exactly is the last one that should trigger and the least one that should trigger, and then a good sampling in the middle. That should be good enough to make sure that this works the way we think it is. Now, if we go ahead and run this, we would expect that this test is actually not going to fail because we actually used the empty string just a little bit ago, and that did not fail. So let's find out. I like to keep my Test Explorer not docked. And notice too that it gives us actually multiple entries, one for each one of those options that we had in there. So again, guesses should be empty at the start of game, passes. This one fails because we really don't have any restrictions on the constructor in this game logic. So let's go find that constructor there. And let's go ahead and add a little test. If secret.length is less than 5, throw new argument exception. And we'll say the secret phrase must be at least 5 characters. A little bit of explanation of what the argument problem is. And then up here in our summary, the secret phrase to guess should be 5 characters, 5 or more characters. And we probably want an exception to be documented here as well, which is a system.argument exception. And we'll say the param ref of name secret and that's a self-closing tag is 5 or less characters. So we will get that exception when this condition is met. So that gives us the documentation. That adds that little bit of logic there. We go ahead and run this again. And notice 1, 2, 3, 4, 5. The 5 characters actually doesn't throw because we didn't do a probably our greater than. And also notice that guesses should be empty at the start of game is now failing, which demonstrates one of the principles we want in our testing is we want the tests to be independent. So this basically we should make sure that what we supply here is good enough to pass. So 1, 2, 3, 4, 5, 6 characters. That should make sure that that still works. And if we go back, this is what's failing. 1, 2, 3, 4, 5. This is exactly 5. And if I go back to the game logic, if secret.length is less than, should be 5 or more characters. Actually, the way that I wrote this up here is exactly what it is there. So my test probably should be shortened by 1, so we have 4. So as long as there's 5 characters, we say that's okay. All right, so that kind of gets us through a little bit of our secret. Let's go ahead and take a look at our, what do we want to take a look at next? Game logic, anything else that should have an initial value. We did previous guesses should start empty. Wrong guesses should probably start at 0. Let's go ahead and do that one. So again, we create a game logic. And we need to supply secret phrase, which is at least 5 characters. And we want to check that the number of wrong guesses is equal to 0. So we're going to use assert.equal. And there's a lot of variations on what this is, but basically all of them take the expected value and then the actual value. So the expected value is 0, and the actual value would be our game.wrong guesses. So that should test that that starts at 0. And we need to go ahead and mark this as a fact, because we're not taking any arguments into this, and we want to make sure that that's run as a test. So that's wrong guesses, previous guesses. Is 1 is lost, and in progress. Initially, we would expect those all to be false, except for in progress we'd expect to be true. So we'd say public void new game should not be 1. And this is a Boolean value, so we actually have Boolean asserts. We would expect this to be false. So we would take our game dot is 1, and we would expect that to be a false value. And this also is going to be a fact. And we'll do the same thing for public void new game should not be lost. Expect that to be false. And public void new game should be in progress. In this case, we expect this to be true, so we're going to use an assert.true instead. Game dot in progress. And secret. Okay. So, and that needs to be a fact. That should wrap up those. That is most all of our properties. Revealed phrase and wrong guesses. Sorry, revealed phrase, and we don't actually reveal the secret phrase. So we would expect, let's do some logic about the secret phrase. Secret phrase should match provided secret, and maybe not match, maybe we should say encode, because we're changing what it looks like. We're basically doing, let's do this as a theory, and let's provide a string secret. So what would we put in our inline data? We would put strings that are going to be examples. It's a hot time in Old Town tonight. Oof. Interesting one. Line data. The classic computer scientist here. Hello world. And like Jacob. Jingleheimer. So just a couple examples, but what would we expect these to actually translate into? Well, I didn't do myself a favor here, did I? But let's go ahead and do this. We'd expect that I to be a lowercase or an underscore, the T to be an underscore. Traditionally, we leave punctuation alone, so we'd leave the punctuation there, and spaces would also be left alone as spaces. So we'll go ahead and for each one of these, we'll replace the character with the underscore. That'll leave us with the exact count and the exact number of spaces. So it's a bit tedious. I probably could have done this with far shorter phrases. In fact, if you want to use shorter phrases, feel free to. And we'll need to add a second argument, which is going to be a string call it revealed to kind of match what used in the game logic. And now we'll go ahead and create our game logic again. This time we'll pass in the secret argument, and then we'll do an assert equal. We want to compare the revealed that we said should be our revealed with game.revealed phrase. But remember, this revealed phrase is, go back to our game logic, actually going to be a string. Yeah, so that should work for us. And should do our test. Let's go ahead and run that one, see what comes out of that. So notice we now have 3 there. If we go ahead and run this, we had 2 pass and 1 fail. And if we look at what failed, notice that we encoded this punctuation as an underscore. So we found an error in our logic. If we go back to game logic class, we're checking for spaces, but not for punctuation. So this is actually not sufficient enough. So what we might actually do here is, instead of checking to see if that's a space, C# does define an isLetter method for the character class. So char.isLetter, and then we pass in a character. It will tell us if that's actually a character code, or if that character code is for a letter, or if it's for something else. So we'll say if char.isLetter, and grab the secret at that particular spot. Then we're going to go ahead and say the revealed phrase at that spot is going to be our secret. And otherwise, or sorry, other way around. So if char is a letter, we want the revealed phrase to be the underscore. I'll just flip those around. So if it's a letter, we set it to be a underscore, and if it's not, we'll go ahead and just carry whatever punctuation happens to be there across. And another closing print there. All right, so that should hopefully take care of that problem. Every so often we should go ahead and run all of our tests, because as we're making changes to our code, it is possible that a test that was previously passing might stop passing now because of some change we made. In fact, we've already seen that, because when we made the change to require at least 4 or 5 characters in the secret, our very first test we wrote stopped passing. And it looks like all of our tests are passing now, so we are in good shape, and we fixed what could have been a major bug in how our game actually works. So I think we've kind of wrapped up all of the concerns about initially creating the game. Now we're going to take a look at actual playing of the game, which is all done with this guess method. So we're going to guess a character, and we should, for example, know that it was added to our list. We should know if it actually got more of the phrase revealed, and we also should check that if it's a character that's not in our game, that is not going to pass. So let's go ahead and do a public, add another method here, public void should guesses should be added to previous guesses. We'll create our game logic. Game. And we'll go back to using secret as our word. And then we'll go ahead and try to guess. And we could pick really any letter we wanted to here. So let's just guess an S. And actually guess needs to be a character, which is single quotes in C#. And then we will want to assert that the collection of guesses now contains that character. So we can do that with assert.contains, and we pass in this case, a character, which would be S, and we want to make sure that that is in the collection, which is game.previous guesses. In fact, it might make more sense to make this a theory, because then we can throw a couple different characters in there, and it makes sense for one of those, or at least one of those to be correct, and for one of those to be wrong. So F is not in secret, S is. And then we'll just make this guess and guess. So that way, it doesn't matter if it's a correct guess or a wrong guess, it should end up in the previous guesses. Let's do another one, public void, and let's do wrong guesses should increment wrong guesses. So again, we'll make a game logic. Game equals new game logic secret. And then game.guess, and we'll make a wrong guess. So maybe W character. And then we'll check that game.wrong guesses, we know because we're incrementing, should be one more than it was previously, which we know it starts at 0. So we'll do assert.equal. So now we know this should be one wrong guess. And let's do F is not in secret. And F X is not in secret. I is not in secret. U is not in secret. E is not in secret. And R, no, R is in secret. I is not in secret. Okay, and we don't want to go over 7 because we know 7's where the game is supposed to end. So we only really want to worry about the legal values. We'll make that a fact. Now we also know that after 7, we should be at the end of the game. So it might be tempting to assert that here, but notice this test is just saying that we should be incrementing. So we actually want a separate test. It's important that we actually keep these things separate because that gives us better feedback when there is a problem. So we'll say public 7 wrong guesses should end the game. But since I already wrote all these, I'm just going to go ahead and copy paste them down here. Only now I don't want to be doing these assertions because that's not what I'm concerned about, but I do need to make 7 wrong guesses. After 7 wrong guesses, we should be able to assert that game.end progress should be false, and I'm going to also check for, we should do that in another test. We really should keep these separate. So 7 wrong guesses ends the game. It's a fact. And then seven wrong guesses loses. Is lost. And since they really are opposite of each other, go ahead and do false game dot is 1. Yeah, in the game with a loss. Okay, I told you shouldn't do this, but since these are all just very related properties, let's just go ahead and throw one test. All right, and public void. Then also, we should have public void correct guesses should win game. We'll do basically the same thing. Game logic equal game equals new game logic secret. If we guess these characters, game.guess s game.guess e game.guess c game.guess e game.guess r guess t. And if you're paying attention, you should realize that game.guess.e, we shouldn't have to guess e twice. So come back to that one here in a second. And then we want to assert that the game is won. So assert dot false, the game should not be in progress anymore. And assert dot true, game dot won is won. And assert dot false, game dot is lost. Okay. So we shouldn't need to guess E twice, but we're going to come back to that idea. Let's go ahead and run our test and see, make sure everything's still passing. And the new ones we've added work as well. Okay, looks like all of those are passing. So let's write a test to actually make sure that we can't or won't be making a problem for us if we guess the same thing twice. And we'll say should not count. We'll just call it should not count. So if we have a game logic game equals new game logic. And let's go ahead and game.guess. And since we know E is in there twice, let's do, well, it actually doesn't matter. Let's do S. And just to be sure, assert dot equal game dot wrong guesses. So this should be 0. Nope. We do that. Actually, let's not look at wrong guesses. Let's look at previous guesses. Previous guesses dot length should be 1 at that point because we have one previous guess. And might be count. Previous guesses is a character array. It is length. Be an integer about not use assert dot equal to check for collection size. Yeah, assert dot single. Because so that's an assertion that looks to see if there's just one in there. And because that's actually a character array, we're going to go ahead and use this equal. It's telling us that maybe this isn't the best thing to do there, but actually in this case it is because we are using an old school array, not a modern IEnumerable based collection. So we'll go ahead and do that, and then game.guess as if we guess the same thing again. Then we should assert.equal. It should still be assert.equal 1. Game.previous guesses.length should still be 1. Now, after we've done that twice, let's go ahead and guess wrong. And let's guess A, which is not in secret. And then we can check game or assert. And we should have 1 in the game.wrong guesses at this point. As we know it started at 0, we actually have a test for that already. So now we've made 1 wrong guess, game.guess. And if we guess A, again, we would expect that the wrong guesses continues to be 1. Okay, let's try running that new one we just added. And notice that it actually fails. And if we go in, we expected 1, we got 2. That's basically telling us that we are actually counting multiple guesses more than once. So let's go back to our game logic and go ahead and address that. So, and you can see we immediately add the character to the guess, regardless if it's already been guessed. So what we could do, guesses is a list, and lists have a contains, contains, and then we give the character C, and let's put this in an if. So if this returns true, it means that that character is already in our guesses. So in that case, we would just return and not add it to our list of guesses. And we need to return a Boolean, true if the guess was correct, false if it was not. So we might change our logic here a little bit. We might just go ahead and make this be a void instead of returning a value, because I don't believe we're actually using that in our program. Now we just invoke guess. Oh, okay. So we are using it, and we're using it to determine that. But let's modify or think about this a little bit differently. Add a new class. And we'll create a guess result enum in our testing exercise project. We have correct, wrong, multiple, and anything else we could say about guesses, maybe not legal. Or maybe a not letter. There we go. So now we have multiple things. We'll go ahead and change our game logic guess to return that. So we'll say we're going to return a guess result. And here we would say return guess result dot multiple. And down here, if guesses, and we'll return. Didn't find it. That was wrong. And we'll return guess result dot wrong. And otherwise, we know it was correct, so we'd return correct. And in fact, we could take out this else because we have a return in this if statement. So as soon as we hit that, we'll stop execution there. So it's really up to you as to whether you want that else to be there or not, because it's logically equivalent either way. And then we have to go back to our program because now this is going to complain. We are going to replace this with a switch statement where we take result of invoking game.guess, and then we'll do our different cases. So case game guess result dot correct. We'll do our console beep with that line, and then we need to add a break. And case guess result dot wrong. We would this beep and say, oh no, things are heating up. Break. And case guess result dot multiple. I'm going to use the same beep and take this thing, and here you already guessed that. Then we added one more, case guess result dot not letter, and we'll do the same error beep again. That wasn't a letter. Which also begs the question, are we rejecting guesses that are not a letter? So if we go back to our guess in our game logic, we're checking to see if we've already guessed, but we're not checking to make sure that this is actually a letter. So we might add that as a second if statement here. If, actually I might do this right at the top, before we even see if it contains, because if it's not a letter, there's really no reason to check. And again, we do that with care is letter D. Okay, after we've done that, we should be able to run this one, and it should pass. And we should also add a test for guessing a non-letter character. So make that one a theory. Guess should be a letter. And let's do a character. And our inline data would be character that is not a letter. Let's do bang. Let's do a number. Let's do ampersand, just a couple. Enough to be representative. Then we'll do a game logic class again. and declare it to logic and secret phrase. We'd expect the result of this to be yes, result dot not a letter. And we could go ahead and also assert on these where we're doing it multiple times now that the expected value would be guess result dot multiple, and we can still check the number of wrong guesses, and because that's going to also be part that we want to make sure that that's not changing on us. So that just means we're being thorough, and here we also want to see multiple. And up here where we let's go ahead and just add another fact for public void correct guess should return correct enum value. We'd expect the result of running that would be guess result correct. And we fact. And we'll do the same thing for an incorrect guess. We'll guess something that's not in secret, like W. That covers those cases. So we've really covered a lot of ground here, and we've changed a little bit of our game logic as a result. So in our game logic, for example, here, we're not returning true. We're instead returning a guess result value. Okay. Now, there's one more thing that if we think about those guesses, we probably want our guesses to be case insensitive. Public void guesses should be case sensitive, which means that if we guess A, that should count for both capital A's and for lowercase a's. So we'll do this game logic game equals new game logic. Let's do a capital, or yeah, secret with a capital S. So we should be able to game.guess a lowercase s, and that should be correct. So just go ahead and check the return value equals, or assert.equals expect that value to be guess result dot correct. And then let's do one more. Assert dot equals guess result correct, and game dot guess. And let's do an uppercase R. So if they have the caps locked down or they shift R, that should go ahead and catch that too. I wrote this in the game logic, not in the game logic test, so we will move that to where it should be. And game logic tests is down at the bottom. Oh, and this is assert.equal. Assert.equals is an older syntax that has been depreciated. So we'll go save all of those changes. We go back to our test explorer and run all of our tests now. We notice that we're actually getting quite a few things are not passing now. So one of those changes we made has, looks like when we run this enum one, for example, we expect correct, and we're getting not a letter. And that maybe suggests if we go take a look at our game logic, we added this test, if char is letter, return not a letter. We actually want to invert this case. We want to say when it's not a letter. Let's save that, run those tests again. This shows how one small change can break a ton of tests, and why it's important to go back and rerun those tests. Every time you make changes, there's actually, we call that practice regression testing, to go back every time you make a change, make sure that that change hasn't broken anything that you were already testing. It's also a really good strategy for doing development work. And now they're all passing except that this should be case insensitive. So if we go back to our game logic, we are checking to see if the secret phrase is that particular character. That's not a case insensitive comparison. That is, that character has to be exactly that particular one. So the easiest, or really the only way to get around this is to convert this character to an uppercase character with char dot to upper or to lower. We just need to make sure that both characters are converted that way to the same value. So char dot to upper. So if you prefer going lower, that's fine too. If we save that and rerun our test, and that passes, we rerun all the tests, we can make sure that they all pass. It looks like they're all due. So we've now written a pretty comprehensive unit test to test this game logic unit. Now we could go ahead and potentially write one for our renderer and potentially for the program as well, but that's really kind of really displays what we're after. So this is a good place to stop here. Go ahead and play the game a few times, make sure that it works well for you playing it as kind of an ad hoc test as well. But that should wrap us up for today. So we'll talk to you later.